John Whitacre. He's CEO at Stratus Materials, and the talk will be about stabilized Cobalt-Fee lithium-rich cathode materials.
Great. So thank you so much for the invitation to speak here. I really appreciate it. I really enjoyed the prior talk as well. And I'll just jump into it. So and just to mention, I'm Jay Whitacre, not John Whitacre. I'm also a professor at Carnegie Mellon University, though I'm currently on partial leave running Stratus Materials, which is a startup in Pittsburgh, Pennsylvania, focused on incepting and scaling the production of a sort of novel process to make stabilized lithium-rich cathode materials. So obviously, preaching to the choir, I don't want to spend hardly any time on the background here, but obviously cathode materials are critical to our supply chain, and we need new ones that are lower or have no cobalt, that are safe, that are less expensive, that can compete with both in terms of safety and energy density and performance with the dominant two players, which is nickel-rich, nickel cobalt manganese oxide, or lithium iron phosphate, lithium manganese iron phosphate. And for years, we've been looking at the potential of using lithium-rich, manganese-rich cathode active materials. And the benefits are clear that it's super appealing that you can have very high energy densities, over 1,000 watt-hours per kilogram at a material level, demonstrated many times over. It's got good thermal properties. It's typically stable to a pretty high temperature, even when fully dilithiated, higher than the nickel-rich materials. And a lot of oxygen is not emitted. When it does, they're really decomposed. So it's got some safety advantages, more similar to LFP. It's lower cost if it's manganese-rich and nickel light and has no cobalt, especially if you can make it with no cobalt. Is a lot of promise there. But historically, there's been some real challenges. It's a complex and poorly understood material in general. The phase that's produced is some superposition of two different crystal structures. Sometimes they're in nanodomain phases. Sometimes it's some sort of a superlattice structure that exists. And upon the first charge, that structure changes, and it's difficult to understand exactly what's happening, and it's very deeply related to process as well. It typically has poor stability over tens or hundreds of cycles. I've missed a word or two there. I apologize for that. And that stability challenge typically is similar to what is seen in the disordered rock salt system, in that it oftentimes will collapse into a spinel phase that has about a 3-volt plateau, and that in general can lead to other structural issues in manganese dissolution as well. So you don't really want that collapse to that spinel phase if you can avoid it. And the materials often are lower energy density, lower physical density, because carbonate precursors are frequently used to produce it. And that gives you lower watt hours per liter at a cell level. And that's always been a challenge as well. And the other two things: diminished rate capability. It's a lower diffusivity material than the high nickel materials. And so oftentimes it's associated with being rate limited, and at usable rates like C/2, C/3 that you might want for an electric vehicle. It's thought to not be able to meet demand. And lastly is the fear and sometimes evidence of excessive gas evolution during use. And so if you can overcome these historical issues with a lithium-rich, manganese-rich system, you are maybe in a really good place. So what we have done at Stratus over the past 3 years, this sort of started as a side project during COVID for me and has evolved into this company now. We have found that a super fast thermal process, so a very fast quench process, specifically at the very end of the process, creates a stabilized crystalline system in the material. And this can be applied both to more traditional PCAM, sort of spherical co-precipitated precursor base material, as well as single crystal material. And if you can figure out how to get that stabilized material into a good densified thick format electrode, you can absolutely create batteries that compete very favorably with existing technology. We are demonstrating this at what we call a pre-pilot scale right now, which is a 10 kilo a day sort of throughput. And our pilot line, which is on the multiple hundreds of kilograms a day, is being erected presently. We intend to turn that on sometime in the June timeframe. The attributes, I'm not going to waste too much time here, but we are similar in safety to LFP, similar in cost to LFP, similar in energy density to NMC, a lot of cost reductions and a lot of other advantages that can be had. So just dive into some data.